Howdy. Howdy. Good afternoon, y'all. Thank you for being here. I hope y'all had a good weekend and hope your Monday is off to a good start. And it's going to get even better because today we are going to be talking about multi-group diffusion theory. Um, so let us begin. Just to kind of like recap where we left off last time. Um, Last time, and also like in our couple earlier lectures, we mentioned some things that that help us highlight the importance of energy dependence of our neutron population within the framework of nuclear engineering. So we saw cross-section plots, and on the vertical axis, it's that cross-section with like units of barns, and on the horizontal axis, it's the energy of the neutron that is participating in the reaction. So those cross sections are a function of the incident neutron energy. We also saw that for those cross sections, like the fission cross section for uranium 235, that cross section is a lot higher when the neutron has a low energy, and then that function decreases as the energy of the neutron increases. So fission reactions, for example, are more likely to be caused by a neutron of a low energy. When we calculate a reaction rate, it's a cross section multiplied by a flux. And so that means that our reaction rates are also neutron energy dependent. And yeah, so those things are really important to describe like where is it more likely for a fission to happen. Also, the neutrons that come out of fission with a distribution of energies. That was what that chi of E, that fission spectrum, was showing us. And from that chi of E, we know that the neutrons can be born from fission with like any range of energies, but that the most probable energy is around 1 MeV. So that's relatively fast. It means that when neutrons come out of fission, they're coming out pretty fast. And if we want those neutrons to be very likely to cause a new fission, then they need to be thermal. And that means that we need to find a way to make our fast neutrons slow down to thermal energies. And we call that slowing them down or moderating the neutrons. So when you hear the phrase like a neutron moderator, that's what we're talking about. It's some material that is good at getting neutrons to slow down. And we're going to learn more about this today, but the way that neutrons do slow down is through scattering reactions. And so we're going to take this information as well as what we've learned from one group diffusion theory to start developing a model for multi-group diffusion. And so at first, instead of letting our scalar flux have dependence on energy, like instead of trying to find a function that's both a function of position in the reactor and the energy of the neutrons, we're just going to discretize the energy range to be two groups. So, like, if E is our energy axis, instead of the energy being a continuous variable that we evaluate at like every single energy E, we're just going to break our energy axis up into two groups. And so we're going to have a fast group and we're going to have a thermal group. And what we want to do, if we want to develop diffusion equations for these particular groups, we need to use conservation and we need to think about what are all of the different gain and loss mechanisms for neutrons in each of these groups. So we're still dealing with nuclear reactors. Nuclear reactors have fission events, which are how we get new neutrons to be born. And fissions can cause neutrons to be born into either group. So both within the fast group, I'm going to say one of our mechanisms is production. And within the fast group, I'm going to put a plus sign here to remind us that production would be a gain mechanism within the fast group. And we can also have neutrons be born in the thermal group. So I'm also going to say production with a plus sign for the thermal group as well. In both the fast and the thermal group, neutrons can be added to that group by fission reactions. And just like when we had one group diffusion, the way that neutrons would be lost is by being absorbed by something in our reactor. So absorption is going to be a loss mechanism. So I'm going to use a minus sign for a loss mechanism. And that can happen also in both groups. So I have absorption as a loss mechanism for both the fast group and the thermal group. And also, when we did one group diffusion theory, the other way that we could lose neutrons is if they leaked out of our system. And so the net leakage would be considered a loss mechanism, and we could have net leakage from fast neutrons leaking out of our system or from thermal neutrons leaking out of our system. So I'm going to show like an arrow going out, and this would be my net leakage. And that net leakage would be a loss. So that's a minus sign, and we can have net leakage out of both the fast and the thermal groups. So yeah, production is a gain mechanism, absorption and net leakage are loss mechanisms, and that holds for both groups. And the way that this is going to be different than one group diffusion is now that we have two groups, we have the possibility that a neutron that's fast could have a scattering reaction, which would lower its energy and then send it into the thermal group. So I'm going to draw an arrow going from the fast group into the thermal group. Um, and also, a neutron that's thermal, a neutron that's in that slower energy group, could have a reaction that increased its kinetic energy that would kick it up into the fast group. So I'm going to draw an arrow that goes from the fast group to the thermal group as well. But I'm drawing that arrow smaller on purpose to just remind us that it's much more likely that neutrons scatter down to a lower energy than it is that they scatter up into a higher energy. So these back and forth arrows represent my scattering. And it could be a plus or a minus because like if I think about the arrow, if I'm looking at the fast group and I'm down scattering, that's a loss from the fast group, but it's a gain into the thermal group. And similar story, if I'm talking about going from thermal to fast, those upscattering reactions would be a loss from my thermal group, but then it would be a gain for my fast group. So these are the only reactions that we would have to consider if we wanted to set up like a two-group diffusion model. The only real new thing that we have going on is the scattering events, which can kind of kick neutrons from one energy group into another when they scatter. And we just define the ranges of these energy groups. So like E is our energy axis, going to the right would be larger energies. So we use E0 to represent like our maximum energy. And then as the neutron energy decreases, this index goes up. So E2 would be like the minimum energy. And that might be it might seem confusing. The reason that we use kind of like backwards indexing, that the smaller index corresponds to larger energies, is because that's where my neutrons are born. My neutrons are most likely to be born at higher energies, so lower indexes. And then as the neutron goes through its life in the reactor and slows down, those higher energies, those lower energies correspond to higher indexes. Um, and so this is the kind of framework that we want to use to think about what our gain and loss mechanisms are. It also kind of helps us start to see that in this kind of formulation where we have two groups, there's coupling between our processes in that the fission events and my neutron production is coupled because fast and thermal neutrons could cause fissions. Um, and neutrons can also be born from fission with a variety of energies. And then there's also coupling by the scattering mechanism because high energy neutrons can scatter down into the low energy group, and low energy neutrons could also possibly scatter up into the high energy group. So to do this derivation, it's going to be kind of like I'm calling it a heuristic derivation in that we're kind of simplifying the derivation process. It's not going to be as rigorous as the way that we like started one group diffusion, but it's going to get us to the same equations that we would end up with. And so in this model, we're just going to assume that each group has constant material properties. So the diffusion coefficients or cross sections of any type, they're going to be constant within each group. We're going to assume that we've like properly averaged those cross sections over the energy range of the neutrons that correspond to each group. And then we're going to assume that we can break up our total energy dependent scalar flux. We're going to assume that we can break this up into two parts, where I have I'm going to say phi1, which is a function of r and t, plus a phi2, which is also a function of r and t. So I'm basically assuming that this total scalar flux can be broken up into two parts. The phi with the subscript 1 would be corresponding to my fast neutron scalar flux. My phi2 would be corresponding to my thermal group scalar flux. And if I were to add those two things together, it would give me the total number of neutrons of all energies that are making path length per unit volume per unit time in my reactor. And in terms of the production, instead of having our fission spectrum be like a probability density function that we evaluate at lots of different energies, we only have two groups. So we're just going to assume that there's a fraction of my neutrons that are born into group 1, and there's a fraction of my neutrons that are born into group 2 when we have fissions. And so I'm going to use chi1 as the fraction of neutrons that are born into group 1 from fission. And I'm going to say plus chi2, where chi2 is the fraction of neutrons that are born into the thermal group from fission. And these are both fractions of the total number of neutrons that are born. So that means that these two fractions have to add up to give me 1. And that, yeah, like it's probably a lot more likely that my neutrons are born into the fast group than into the thermal group. So maybe chi1 is like 0.9 and chi2 is like 0.1. But whatever those two things are, they have to add up to give me a 100% probability that accounting for all of the neutrons that are born out of fission. And then thinking about our speed, because these are groups of neutrons that have like kind of a range of energies, if we want to talk about the speed of the neutrons in each group, we'll just use a V1 and a V2, which will represent like the average speed of the neutrons in our groups. So thinking about the picture that we drew that shows what our gain and loss mechanisms are, we can start thinking about a conservation statement that we could use to develop a mathematical equation that we could use to then learn something about this distribution. And so what that conservation equation would look like is it's going to say rate of change per unit volume. Rate of change in this case of my neutron population per unit volume equals all the ways that I could gain neutrons, my gain rates per unit volume, minus all of my loss rates per unit volume. And we had kind of already set this up when we did our plus and minus signs, that production is a gain rate for both groups. Absorption is a loss rate for both groups. Net leakage is also a loss rate for both groups. And then the scattering reactions can either be a gain or a loss, depending if we're talking about in scattering or out scattering. So if we're looking at one particular group, if neutrons scatter into that group from another one, then that's a gain mechanism. In scattering would be a gain mechanism for that particular group that we're looking at. And also if neutrons scatter out of that group into another group, then that would be a loss mechanism for that group. Um, so yeah, in terms of the losses, we've got leakage, we've got absorption, and we've got outscattering. And then in terms of gains, we've got fission production, and we've got inscattering. So if we know what those quantities are and we know how to express them mathematically, then instead of having that equation in terms of words, we can have expressions for those different quantities, and then we can have an equation that we can try to solve. So I'm going to start writing out what some of these loss terms are for each group. And so if we think about the net leakage, that is going to look just like the net leakage term that we have in our one group diffusion equation. So it's going to look like minus the diffusion coefficient. And I'm going to say, because we're doing this for the fast group, I'm going to do a subscript 1 to remind me that this is the diffusion coefficient for group 1. And then times the Laplacian of the flux also for group 1 neutrons, and that flux can vary with position and with time. right? That looks just like the net leakage rate density for one group diffusion. And all I'm doing is adding subscripts 1 on the diffusion coefficient and the flux to just remind myself that this is just the loss, the net leakage term for group 1. If I wanted to write the net leakage rate density for group 2, what do y'all think that's going to look like? Same thing with subscripts 2, right? So I'll have minus the diffusion coefficient for group 2 times the Laplacian of my scalar flux in group 2, and that flux can vary with position and with time. Perfect. So those are what my net leakage terms are going to look like. And then I'm going to have I want my absorption rate density too. And if I wanted the absorption rate density, what two quantities would I multiply together to get an absorption rate density? Perfect. Yeah, macroscopic cross section of absorption times the flux. So I'm going to say sigma A for group 1 times the scalar flux for group 1, and that would be my absorption rate density for my fast neutrons. And then I would have a similar term for my thermal neutrons, which just subscripts 2. So this would be sigma A for group 2 times the scalar flux for group 2, and that flux varies with position and time. So those are what my absorption and my leakage terms are going to look like. And these are all rate densities. So what are the units of all of these terms going to look like if it's a neutron rate density? They all have neutrons in the top, and it's a rate, so that means that it's per unit time. So I'm going to have like units of seconds in the bottom. And it's also a density. Like if you think about mass density, it's like grams per unit volume, like grams per centimeter cubed or grams per meter cubed. So if it's a density, it also has units of centimeters cubed or meters cubed in the denominator. So all of these quantities have units of neutrons per unit volume and per unit time. So that's my leakage and my absorption terms. And the next thing I want to talk about are my fission production terms. We have already talked about the fraction of neutrons that are born into each group. That would be my chi1 and that's supposed to be chi2. Sorry about that. Typo in my notes. That 1 is supposed to be a 2. Um, and so within each group, we also have constant material properties. So we'll have like a nu F and a sigma F for each group. When we write a fission production rate density, if I wanted to ask you about what would a fission production rate density look like, the nu F times times the flux, that would be my fission rate density. Cross section times a flux gives me a reaction rate density, and if it's a subscript F, that means it's a fission cross section. So that product is my fission reaction rate density. And if I multiply that by nu sub F, nu is the number of neutrons per fission. So if I take this quantity and then I also multiply by nu sub F, it turns it from a fission rate density into a production rate density, and that now it has units of neutrons per unit volume per unit time. So like in general, this nu F sigma F phi is what my production rate density is going to look like. Except now I have two possible energy groups where there are neutrons causing fissions that could be contributing to the overall production rate density. So I'm going to have in the I'm going to kind of go off to the side and I'm going to start writing my my production rate density terms. So neutrons from the group 1 could cause fissions. So I'm going to have a nu F1 times a sigma F1 times a phi 1. And that represents my production rate density of neutrons causing fissions. These are all of my fast neutrons that are contributing to my fission and therefore to my neutron production. And then I would also have a nu F2 times a sigma F2 times a phi 2. And that second term represents all of the thermal neutrons that are participating in fission reactions that are producing neutrons. So this in the brackets, that's like my total production rate density. It's the neutrons that are in the fast group and the thermal group that are contributing to my fission reactions. And that's all of the neutrons that are being produced, but only a fraction of those are going to be born into the fast group. So I just need to take this and hit it with a multiplier that says of the total, what fraction of those get born into group one. And that's exactly what chi1 is. So I'm going to take this and I'm going to hit it with a multiplier of chi1 because that's what chi1 represents. It's the fraction of all of my neutrons that get born from fission into group one. And so if that's what the fast production rate density looks like, the thermal production rate density is going to look the exact same, but I'm just going to have a chi2 up front instead. So here I'll have chi2 times my new F1 times my sigma F1 times my phi1, which is a function of R and T, plus my new F2 times my sigma F2 times my phi2, which is a function of R and T. So yeah, basically each of these equations says the first thing up front is the fraction that's emitted into each group multiplied by the total production rate density of neutrons in the system. And so this is an example of we already saw this when we saw our little picture that we drew, but mathematically this is also helping us see that there's coupling between my different energy groups and that fast and thermal neutrons can cause fissions. Some of those fissions will result in neutrons being born into group one. Some of those fissions will result in neutrons being born into group two. So the main thing that we haven't, those are all things that we've kind of already talked about in some detail. The main thing that we haven't talked about is scattering. So that's what I wanted to start getting into. That's like kind of the last term we need to build out to have our model be complete. When we had one group diffusion, there was no scattering mechanisms that we needed to keep track of because there was only one group. And if you scatter, you you can't scatter if you only have one total group, then you can't scatter out of that group or into that group. Every scattering event would just be like a within group scattering that wouldn't add or lose neutrons from the entire system that we're keeping track of. But now there's two groups, neutrons can get kicked from one group to another, and that's another example of coupling between neutrons of different energy groups. Scattering reactions and fission reactions result in coupling between neutrons of different groups. And so just like with fission, where there's a probability distribution that describes how likely it is that a neutron is born from fission into a particular energy, there's also a probability distribution that describes the energy distribution of scattered neutrons. That some neutron with some energy can scatter, and we want to know what's the probability distribution that it ends up with some certain energy after the scattering event. And so to calculate our scattering rate densities, we need our scattering cross-section, and we also need that probability density function. So I'm going to define that probability density function as P of EI to EF. And if I take that P of EI to EF and I multiply it by DEF, then this entire quantity is telling me about a probability that a neutron scattering with an initial energy EI, that it emerges from that scattering reaction with a final energy EF within the interval DEF. So I'll say with final energy in that interval in DEF about, or you could think of it as around the final energy EF. So this is a probability density function that gives me information about what's the probability that a neutron comes in with some energy EI and gets kicked out with some energy EF. And if we knew what that probability density function was, then we would have everything that we needed to put our equations together. So we can do like a simple scattering experiment that could help us understand what that distribution might look like. Here we're going to kind of think back to that thin target where we had a thin, cold target and we were shooting neutrons at that target. And those neutrons were like in a beam, like a monodirectional beam. So all those neutrons had the same energy, and we'll call that the incident energy EI. They're going to scatter with this target. And then now we're going to put like energy sensitive detectors around the target so that once those neutrons scattered and hit the target, we could figure out what energy those resulting scattered neutrons had. And if we knew that, then we could construct a probability distribution that would look something like this. So this on the top is my probability density function. The P from EI to EF with the capital P is my probability density function. And because it's a probability density function, it has units of like inverse energy. So like it has units of 1 over EV. And then on the horizontal axis, this is my final energy axis. So it's like I'm looking at my detector and then I'm monitoring what are the resulting energies of the neutrons that are coming out of that scattering event. And so if the neutrons are coming in with an energy EI and they're scattering with like a cold stationary target, is there any way that those neutrons could gain energy in that collision if they're scattering with a material that's cold? Cold meaning that it has like no vibrational kinetic energy. Its vibrational kinetic energy is basically zero and it's stationary. Can the neutrons gain energy in those collisions? In terms of like conservation of energy, if we wrote scattering is just like billiard ball collisions effectively. So it's governed by conservation of momentum and conservation of energy. And so if the neutron coming in has an energy EI and it's scattering with a stationary target, then the energy at the beginning is based on the kinetic energy of the neutron. And if energy is conserved, then the best that we could do at the end is that that neutron had the same energy that it started with. So the neutron can't gain any energy in a collision with a cold target. And so that means that if I think about the maximum energy that neutrons could come out of this event with, the maximum energy here is just the initial energy EI. If it's a cold stationary target, my neutrons can't gain any energy in that collision. So the highest energy they could have is the energy that they started with. And then depending on what the material is that they're colliding with, they they could definitely lose energy in that collision, but they can lose energy just up to a certain point. So I'll just write E min here to say this is the minimum possible energy that we would see neutrons coming out with. And past that minimum, you don't see any neutrons that get scattered into any lower energies than E min. So that's what my horizontal axis looks like. It's kind of just like an energy interval going from from E min to EI. And if this is a probability density function, then we know that the area of a probability density function over the entire domain has to be 1, right? So this area has to be 1. And if I know that the area of this total function of the total area of this PDF is 1, and I know that this is my energy range or like my energy interval on the energy axis, then what does that mean that the height of this probability density function has to be for the area to be equal to 1? This is a rectangle, right? So the area is length times height. And so if I multiply this height by this width and I get an area of 1, then that means that this height has to look like 1 over EI minus E min, right? That's like the width of my interval. And if I do 1 over that width, then if I were to take this as like my height and this distance right here, this interval as my width, and I multiply those two things together, then I'm going to get 1. And also, this is going to have units of inverse energy, right? Which is what my probability density function should have units of inverse energy. And so if this was my probability density function, like if I actually knew what this function was, then I could use that function to set up an equation that told me what was the fraction of neutrons that come out of the scattering reaction with some range of energies, like energies with from energy E1 to E2. And so the way that I would do that is I would integrate my PDF over that energy range. The fraction of neutrons that scatter and come out with energies in this range would just be the integral from E1 to E2 of that probability density function, PEI to EF, integrated with respect to that final energy. So this right here is how I would turn the probability density function into just a fraction. I would take that probability density and I would integrate it over some range. Hopefully that's okay. As always, if there's questions about anything, feel free to stop me and let me know. Um, so once we have some idea about that probability density function, then we can set up what our scattering cross sections need to look like. So in general, when we talk about the scattering cross-section sigma S, that cross-section, like if we were to look it up on Janus or some nuclear database, it's only going to depend on the incident neutron energy. So the scattering cross-section by itself depends on the incident neutron energy. And that was our EI. And if I know that scattering cross section and I know that probability density function, then the product of those two things and also multiplied by that energy interval, the final energy interval, is my by definition, that's going to be my microscopic cross section for scattering to go from the energy EI to the energy EF in the interval DEF. And so, like if we think about the units, then sigma S is just a reaction cross section. So it has units of 1/centimeters. That probability density function has units of inverse energy, like 1/eV. And then I'm multiplying by DEF, and DEF is a energy interval, so it also has energy units. It would have units of EV. And so if I know those individual terms, I could see the EVs on bottom cancels the EVs on top to give me something that overall has units of just inverse centimeters. So the units of this thing would be inverse centimeters. And so when we talk about a macroscopic cross section for scattering from one energy to another, this is really what we're talking about. But a lot of times when you read nuclear engineering, like textbooks and stuff, they'll kind of bake it all into one cross section that looks like this. So instead of seeing a cross section with just one energy argument, it's a cross section that says sigma S from energy EI to energy EF. And what it is representing is the product of my scattering cross section times that probability density function. So this quantity right here is kind of like the typical thing that you'll see in like nuclear engineering textbooks. And this scattering cross section times this probability density function, this has a name and it's called the macroscopic differential scattering cross section. And the differential scattering cross section has units that are based on sigma s and that probability density function. So it has units of inverse length and inverse energy. So it would we could say inverse length per unit energy. So it would look like 1/centimeters times EV, all in the bottom. So if I take that cross section, multiply by that PDF, then that gives me my differential scattering cross section. And that name, differential scattering cross section, might sound kind of scary or confusing, but the name makes sense if you think about what I would get if I took this whole thing. In other words, if I took sigma s from EI to EF and I integrated it over the entire energy range, then going from here to here, I'm just using this definition. So I'm rewriting the differential cross section in terms of the scattering cross section and that probability density function. And then if I look at this probability density function times the scattering cross section integrated over the final energy DEF, then this DEF is the final energy. That means that my original scattering cross section, which only depends on the incident energy, can come out of this energy integral. So if I can pull the scattering cross section out front, then all I have left inside of here is the integral from 0 to infinity of a probability density function integrated over energy. And if I integrate a probability density function over the entire domain of that function, then I just get one, right? So the sigma s comes out front, the integral that's left over is just equal to one. So therefore, this whole thing just gives me sigma s at the incident energy. So in other words, it's called the differential scattering cross section because if I integrate the differential scattering cross section, I just get the regular scattering cross section. And that's kind of like what integrals do. Integrals and derivatives are inverse operations. So if I have a function, I take the derivative of that function and then I integrate that function. If I have a function, I take its derivative and then I integrate that thing that I just got, it's going to get me back to the original function. So that's why they call it that. Um, that's so hopefully that kind of helps us better understand why it has that funny name. Um, so with that being said, this is kind of like the way that we'll end up writing this for the two group case is that so we can think about it like we've got the cross section that goes from E1 to E2, because in this case we just have energy 1 corresponding to like my fast energy range and E2 corresponding to my thermal energy range. And I could look at this and I could say, okay, that's going to be my scattering cross section at that first energy times the probability density for me to go from that first energy into the next energy. And so it's just different notation for basically saying the same thing. Like if you see the sigma s from E1 to E2, we might get tired of writing all these arguments and then just use some shorthand to say, I'm just gonna write it like this instead of writing out all the arguments. So that's all that this sigma s from 1 to 2 represents. Just different ways of writing that differential scattering cross section. Um, and so the other way that we could kind of write this is we could say, at least for this first case, that this is sigma s 1 times the probability to go from group 1 to group 2 in some scattering event. And we could do a very similar thing with our group 2 result, in that this is talking about scattering reactions that go from group 2 into group 1. It's always going to be looking like some scattering cross section at the incident energy, which in this case, if I'm going from 2 to 1, then I'm going to have a sigma s for group 2, and then I'm going to be multiplying by some probability density function or some fraction that says this is how I go from energy 2 to energy 1. And I guess I just want to be careful here because, like on the previous slide, I was using a capital P. And so that capital P is a probability density function. It has those units of inverse energy. Here, when I use a lowercase p, really, this is just a fraction. And so I've kind of said that more here. This p from E1 to E2, or my p from 1 to 2, and then same thing with the p from E2 to E1, and the p from 2 to 1. These are the fractions of neutrons that are going from one energy to another. In other words, I've already, with the lowercase p, I've like already taken that probability density function and then integrated over the range that corresponds to each group. So yeah, that's kind of the difference in notation going from big P to little p is I've already integrated it over the corresponding energy range. So this quantity right here also and this on the left, this is kind of like the shorthand that we're going to use to just categorize the scattering reactions that take me. It's a scattering cross section with units of inverse centimeters, and it includes that fraction of neutrons that go from group 1 to group 2, and also the fraction of neutrons that go from group 2 to group 1. So if I wanted to write equations for my scattering rate densities, outscattering and inscattering, then these scattering rate density, it's a reaction rate density. So it's going to look like a cross section times a flux. And if I want to talk about outscattering from the fast group, then that means I'm going to have a sigma s going from the fast group, which was 1, to the thermal group, which is 2. And if it's fast neutrons that are participating in the scattering reaction, then it's going to be the fast flux that is being multiplied here. So I'm going to be multiplying this by phi1, which could be a function of position and a function of time. So this would be my outscattering rate density for the fast group. I've got my cross section that tells about the cross section of neutrons that scatter to go from group 1 to group 2, multiplied by the flux of neutrons that were responsible for that reaction in the first place. And then the in-scattering rate density is going to be neutron scattering from the thermal group into that fast group. So this is going to look like sigma s from 2 to 1. And then it's the thermal neutrons that are participating in these reactions to kick me into the fast group. So the multiplier here is going to be based on the thermal flux, P2. So that's what my outscattering and inscattering rate densities would look like for the fast group. And then for the thermal group, it's going to look very similar in that my thermal group is group 2. So if I'm scattering out of the thermal group, that means I'm going from group 2 into group 1. So this is going to look like sigma s to go from 2 to 1, and it's going to be caused by those thermal neutrons. So I'll have a phi2 as a function of position and time. And then the in-scattering into the thermal group is going to mean it's going to be dealing with neutrons that are going from the fast group into that thermal group. So I'm going to have a sigma s going from 1 to 2, and that's going to be multiplied by the neutrons that caused this, which were the group 1 neutrons. And so notice here we have more like mathematically illustrating the coupling between our energy groups in that, just like we showed on the picture, anytime that a neutron scatters from the fast group into the thermal group, that's a loss from the fast group, and that exact number is the gain into the thermal group, right? If I look at my in-scattering rate density for the fast group, it's exactly the same formation as the outscattering rate density from the thermal group, because that's saying I have thermal neutrons that are scattering out of that thermal group into the fast group. And if something scatters out of the thermal group and into the fast group, it's a loss for the thermal group and it's a gain for the fast group. And then opposite with the outscattering rate density from the fast group, it's exactly formulated the same way as the inscattering rate density for the thermal group, because I'm getting scattered out of the fast group and all of those neutrons go into the thermal group. And so to kind of put all of this together, the only thing that we need to mention is that we're assuming that if there's a scattering event, then it's kicking the neutrons out of its current group. It means that we're not including any within group scattering. We're not going to consider in our balance equation neutrons that stay in the same energy group when they scatter. So that means that we're basically just assuming no within group scattering. There's no within group scattering. So that means that like the sigma s to go from 1 back into 1 is the exact same as the sigma s to go from 2 back into 2, and it's 0. We're assuming that there's no scattering reactions that keep the neutron in that same group. So we've set up our gains and our losses. We've put together mathematical equations for all of those gains and losses. And then we know what our conservation statement is going to look like. It says the rate of change of my neutron density equals all of my gain rates of my neutron density minus all of the loss rates of my neutron density. So we've developed all of these terms, and now we're just putting them together for each group. And then we're also including the change rate density term up front, which looks just like it did in one group diffusion, but we have the subscripts 1 to say this is the change rate density for group 1 neutrons, and this is the change rate density for my group 2 neutron. So this right here is our two group diffusion equations. And if I go to the next slide, um, this kind of I highlighted these terms so that we can just see with the equations that we've developed the coupling between these two energy groups, and that the green term is my fission term, my fission production term, and it's neutrons from group 1 and group 2 participate in fission reactions that could add neutrons into group 1. Neutrons from group 1 and group 2 can participate in fission reactions to add neutrons into group 2 as well. And then my scattering reactions, they're equal and opposites in each equation. So if I'm looking at group 1, then I have gains into group 1 from group 2 neutrons scattering into group 1. And I have losses for group 1 from neutrons scattering out of group 1 into group 2. And then that outscattering for group 1 is exactly equal to the gain mechanism for my group 2, because anything that scatters out of group 1 goes into group 2. So that means that that term becomes a gain mechanism for group 2. And any neutrons that are being added into group 1 from group 2, so going from 2 to 1, here it was a gain mechanism, here it's a loss mechanism because they're being kicked out of group 2 and they're going into group 1. So these are the equations that we could use to describe the kind of energy dependence in a crude way by solving these equations and then having a flux that tells me about my phi1 flux and my phi2 flux. And if we wanted to solve these, we would also need all of those auxiliary conditions as well. Like we would need boundary conditions because we have a second derivative. The Laplacian is second derivative of our scalar flux function. So we would have second derivatives, which means we need boundary conditions. We also have, in this case, we have a time derivative, which means that we would need initial conditions. We would need physical conditions as well. Like we would need to keep in mind that the scalar flux is still a continuous function and that it's physically realizable. So like it can't be negative. It can't go to infinity. So this is an example of two groups of coupled partial differential equations, and they're coupled because, like, if I'm trying to solve this first equation for phi1, well, in this equation for phi1, I have the variable phi1 and the variable phi2. And same thing for the second equation. I have both my functions are like an unknown in each equation that I have. So these are coupled partial differential equations for that reason. They're mathematically coupled, and then the physical processes that result in the coupling is due to fission and due to scattering. If we wanted to, this is just rewriting those equations. We're saying that we're in steady state, so we're getting rid of that d by dt term. And we in this equation, the way that I'm writing this, if it's steady state, then there's no d by dt term. So I'm getting rid of the time argument on my scalar flux. So now I'm just writing the scalar fluxes as a function of position. But here I'm also allowing that my material properties to change with position. So I've added position arguments on all of my like cross sections and all of my diffusion equations. My diffusion coefficients. Also, notice here that like on this term, and on this term, that instead of writing it as the Laplacian, the triangle with a square, I'm having to rewrite it as the divergence of the gradient. And basically what I'm doing is I'm taking that diffusion coefficient and I'm putting it back inside of the operator, because now if the diffusion coefficient depends on position, before I had pulled it out of that operator because we assumed that there was no position dependence. And then that was where that Laplacian came from. Like if I pull this diffusion coefficient out, then I've got the gradient. Sorry, I've got the divergence of the gradient of the flux, which is the Laplacian. So I'm just kind of putting that back inside of the definition and then writing it based on the original way that we had written net leakage using Fick's law. So that's kind of the only difference with these two sets of equations is I'm just allowing my material properties to change with position, which is a consequence of that. And then I'm also assuming steady state, which is why this d by dt term is basically going to zero. If it's steady state, there's no time dependence on the flux. So this would go to zero and that would go to zero if it was a steady state problem. And that's the only thing that would really change if it's steady state is that those time derivatives go to zero. And then I no longer have to write time arguments on my flux because the flux would no longer depend on time if it's steady state. And then this is just helping us to see how what we've just set up kind of aligns with Dr. Svedkov's notes. So like when we did one group diffusion, we wrote our one group diffusion eigenvalue problem like this. And then we mentioned that this form of the equation looks just like me saying I have this loss operator operating on my neutron population, and that equals 1 over k effective times the production operator operating on my scalar flux. Or operating on my neutron population. So if I think about it kind of like as an operator form, then I can rewrite those two group diffusion equations as in an operator form with my k effective eigenvalue being added. So yeah, this is like the two group diffusion equations as a k eigenvalue as k eigenvalue problems. Um, so yeah, this basically just says my loss operator times my flux equals 1 over k effective times this gain operator times gain operator acting on my scalar flux. And this these terms, the sigma s from 2 to 1 and the sigma s from 1 to 2, those are left out of this production operator on purpose because technically the scattering reactions aren't really producing or losing neutrons. If I look at the system as a whole, all they're really doing is taking neutrons from one group into another. So like kind of if I were to go back here, almost imagining that if I were to add these two equations together, to say something about the total system as a whole, then this scattering term and this scattering term, if I added my equations together, they'd cancel, right? Because this term has a plus sign, this term has a minus sign, and they're of the exact same form. Same thing with these two terms. If I were to add my two equations together, this plus term and this minus term would also cancel each other out. So thinking back to our discussion of the scalar flux, talking about our basically realizing that our neutrons have a distribution both in terms of their position in the reactor, but they will also have a distribution of energies within the reactor. So this is that energy distribution. This is a plot of what that energy distribution would look like for a thermal spectrum reactor, meaning that a reactor where most of the fissions are caused by neutrons that are at thermal energies. Technically, this is a plot of something called flux per unit lethargy, which is very similar to the flux per unit energy. We're not going to define lethargy just yet, but these two, if I were to draw this plot as a flux per unit lethargy or a flux per unit energy, they're going to look very similar and they're going to have the same features. So here on the right, we have the part of my spectrum that corresponds to my fast neutrons. And notice that at high energies, this is where most of my neutrons are born fast, and the birth of my fast neutrons is based on the fission spectrum. So at high energies, this energy distribution looks like the fission spectrum, which is my chi of E. Um, So neutrons are born fast. In that fast region, they look like that fission spectrum. As those neutrons have scattering collisions, which reduce their energy, we're going to the left on this graph. This kind of intermediate range is the slowing down process. And as those neutrons go through that slowing down region, the spectrum, our energy distribution or our energy spectrum follows 1 over E. And we will prove that later, but right now you can just take my word for this. In the intermediate slowing down range, the neutron distribution follows 1 over E. And then as those neutrons are slowing down, what ends up happening is that eventually those neutrons will basically come into thermal equilibrium with the moderator or with the other like reactor materials that are in the reactor. And so as we get to these thermal or low energies, the distribution ends up looking like the Maxwellian distribution. So at low energies, the distribution follows a Maxwellian distribution. And that's M of E. So like this Maxwellian distribution has a peak. And that peak, if I were to think about like the energy of that peak, what this peak energy represents is kind of like the average temperature of my moderator. Like if it's a PWR or a BWR, then it's water is the material that's my moderator. It's the thing that slows my neutrons down. If it's like a gas-cooled reactor that's a thermal spectrum, then it's probably using graphite as my moderator. And so the energy that corresponds to this peak, that is the energy of my basically like if I think about E equals KT, where K is my Boltzmann constant and T is the temperature of my materials in Kelvin, then this T, if I were to think about like the T average of my reactor, of like my moderator, that's what this E peak, oh shit, that's what this E peak, that peak energy is corresponding to the average temperature of the like moderator. So that's what this peak is corresponding to. And as my neutrons slow down, eventually they come into thermal equilibrium with that moderator, and and then those neutrons start to follow that same Maxwellian distribution that we had kind of talked about a little bit in our first couple of lessons. So if this peak is kind of based on, if the energy of that peak is kind of corresponding to the average temperature of my reactor, then how do we think that this distribution would change if we were to raise the temperature of the reactor? Like if the temperature of this reactor was at 500 Kelvin, and then we raised the temperature of the reactor to like 1,000 Kelvin, how do we think this distribution would change if we increased the reactor temperature? If T average goes up, that means that my peak energy is going to go up too, right? Because they're proportional. So instead of the peak energy being right here, it would be shifted over a little bit to the right. So like if we heated the reactor up, what we would see is that this distribution, oh, that's not a very good color. Let me use a better one. Let's use purple. So if we were to heat the reactor up, this would be like if we increase T average, then all that is going to do is going to change what the Maxwellian part of my distribution looks like. These higher energies are so energetically high that like the neutron energies in the intermediate or in the slowing down and in the fast range are so high that the material temperature doesn't really impact what the distribution looks like in the slowing down range or in the fast range, but it certainly influences the Maxwellian because the Maxwellian is what depends on the temperature of the materials that the neutrons are around. So I could ask you something like this, and that would be what would happen if the temperature was increased. You could probably guess that if the temperature of the reactor decreased, it would be the opposite, where that peak would get shifted to the left. So you could also be asked something like that, and it would be a similar story. We would just say that that Maxwellian would get shifted to the left if we had a decrease in the average temperature of our materials. The fission spectrum, this is like a nuclear physics phenomena, right? Like whatever energy our neutrons come out of fission, that is not going to depend on the temperature of the materials. It's just going to depend on what kind of nuclide I have. And like, I guess technically this temperature, and I shouldn't draw it coming all the way down over here. That was just me being a little careless. At some point, the Maxwellian part kind of bleeds into the slowing down part. So these distributions would end up matching up somewhere. So this is showing that same plot, but it's also overlaying it with a plot of the fission cross section. And so we had already mentioned this, but it's good to just write it down that that Maxwellian distribution is there because neutrons come into thermal equilibrium, thermal, I can't talk, thermal equilibrium, with the reactor's moderator, with the reactor's moderator. Um, if your reactor's at room temperature, like 20 degrees Celsius, then that would mean like 293 degrees Kelvin. And so if you do E equals KT, where T is 293 Kelvin, then that gives you the average energy of like a thermal neutron in our reactor. And on homework one, you should have seen that that was about 0.025 EV. So like that is what this peak corresponds to. That's like my 0.025 EV. Um, and this energy for like thermal neutrons is also so low that if a neutron is at this thermal energy, there's a chance that that thermal neutron will scatter off of like hot fuel. And if the fuel is hot, maybe it's at like 600 Celsius or 7 or 800 Celsius. It's going to be a lot hotter than the moderator. And that means that those fuel atoms are going to be vibrating very, very quickly, such that that neutron could scatter with something and kick it up into a higher energy. So in the thermal energy range, upscattering is possible. Upscattering is possible. Upscattering isn't really likely when you're in like the intermediate or the high range. So upscattering really only happens with thermal neutrons. Um, in the slowing down range, we had already said that this distribution kind of follows 1 over E. But notice how this distribution is like pretty smooth in the thermal range, and it's also pretty smooth in the fast range. But in the slowing down range, we have some of these like crazy peaks and valleys and like kind of noisy oscillations. That happens because of the fission spectrum, sorry, the fission cross section and the resonances of that fission cross section. So the deviations occur to resonances. Oops. Resonances in our cross sections. So that's just helping you better understand why there's those weird wiggles. It's because our cross sections are energy dependent, which means our reaction rates are energy dependent, and that means that our energy distribution is going to have some of those artifacts as a result. And then yeah, and fast energies. Oh yeah, and this is also just showing like possible ranges of like where we might consider to say this is my thermal range, my intermediate range, and my fast range. Um, so yeah, it's kind of arbitrary how you set those ranges, but this is just like kind of how I'm defining them here, and also how they're defined on this picture. So we had just written out, or at least we had kind of put the pieces together to get this one group K eigenvalue diffusion equation. And really, I said that we had derived last class. We just derived this. So that we just derived. I noticed that typo this morning and I didn't have time to change it, so I'm sorry about that. But yeah, we just showed that this is what our one group diffusion equation would look like. And we kind of assumed that all of our terms, like our diffusion coefficients and our cross sections, were averaged over the energy range for those group one neutrons. And we used fractions like chi1 and baked into the sigma s from 2 to 1, there was also a probability that our neutrons were like scattered into that group or that our fission neutrons were born into that group. Um, if we want to, we could take this equation and rewrite it using energy dependent quantities where the energy is now a continuous variable instead of having the energy instead of talking about like two groups, we could just use an energy variable E and then have the energy be like a continuous variable. So that's what I was going to write here, is just kind of showing what the corresponding energy dependent diffusion equation would look like. So I'm going to have the negative of the divergence of my diffusion coefficient and I'm going to actually use a bracket here. So now my properties can vary with position and energy. So this is my energy dependent and position dependent diffusion coefficient. And then I'm going to have the gradient of my scalar flux, which also can depend now on energy and on position. That's like the analogous form of that net leakage density term. And in our one group equation, we had like a sigma S and a sigma A, and these represented losses of my group one neutrons that were either being lost because they scattered out of our group or because they were absorbed while in that group. And if I kind of lump these two things together, then my sigma S plus my sigma A is going to give me a sigma T. So this corresponding term in my energy dependent diffusion equation is going to look like a sigma T, which could vary with energy and with position. And then that's going to be just multiplied by my energy dependent scalar flux. So it's a scalar flux that can depend on energy and on position. So that's the corresponding like total interaction rate density term. And then that is equal to, I'm going to put my equal sign right here. It's equal to the gain mechanisms into this group from scattering reactions. So the way that I'm going to write this, if the energy is a continuous variable, is that I'm going to have an energy integral. I'm going to integrate from 0 to infinity, and I'm going to say dE prime, where this E prime is telling me about the initial neutron energy. And so if this is an energy dependent problem, I need to not just keep track of neutrons going from one group into another. I need to keep track of every single possible energy, every other energy, because any of those neutron energies could scatter into the energy E that I'm keeping track of. So I'm integrating over all other energies, which is the E prime, and I'm going to have my sigma S, which is going to be a function of, I'm going to say from E prime to E, from the initial energy to the final energy that I'm keeping track of. And it can also depend on position. And I take that scattering cross section and I multiply also by my flux, my energy dependent scalar flux. So in this case, this is like my scattering my in-scattering rate density, the rate per unit volume per unit time of neutrons that are scattering into the energy group E from all other energies E prime. And then I'm going to have another term which looks like my fission production term, except now I'm going to use chi of E, which is the actual fission spectrum. It's going to have the 1 over K effective. And then here, instead of having production from group one and production from group two, I can say, I'm just going to look at the production into this group of my fissions caused by all other neutron energies. So again, if it's a continuous variable, I have to integrate from 0 to infinity, integrating over all other energies, so dE prime, and then the rest of it just looks like a fission production rate density. So I have a new F, which could depend on the incident energy and position, a sigma F, which could depend on that incident energy and position, and my energy dependent flux as a function of that incident energy and position. So this is what my energy dependent diffusion equation would look like. Notice that these are very similar in how they're set up. They're both conservation statements. They basically both just say, I have all of it effectively says my loss rate densities equal my gain rate densities. So these things on the left side would be my losses, losses due to net leakage, losses due to any interactions that take neutrons out of the current energy E. And then my gains are due to neutrons that are scattering into this current, oh, sorry, this this right here should be E prime because this is scattering reactions caused by neutrons at this incident energy that kick me into the energy E that we're keeping track of. And then I could also have fission reactions from neutrons of all energies that add into the energy group E that we're keeping track of. So yeah, that's what the energy dependent diffusion equation looks like. And it's probably good for us to just talk a little bit about the terms in this equation. So here I've just rewritten that equation and I've spelled out, I've kind of written it out in terms of four terms. Um, this kind of equation, because we have these different, we have the divergence and we have the gradient, that means that these are telling us to take spatial derivatives. And we have integrals. So it's not just a differential equation. This would be an integro differential equation. This is called an integro differential equation. And it has that name because it has integrals and derivatives inside it. This is fundamentally just a conservation statement. And so each of these terms is telling me something about either gain mechanisms or loss mechanisms. And each term in this equation has units that are going to look, well, let's just look at these terms to kind of think about what the units are going to be looking like. So like if I think about my um, the the divergence, that's basically telling me to take first derivatives with respect to space. So it's like d by dx or d by dr. So that has effectively units of 1/centimeters. The diffusion coefficient has units of centimeters. The gradient is also a similar thing in that it's telling me to take another derivative with respect to space. So that's also going to have units that look like 1/centimeters. And then when we talk about the energy dependent scalar flux, it's the same thing as our regular flux, but it's also a density and energy. So it has units that look like neutron path length per unit volume, per unit time, and per unit energy. So if I think about the units now, those are the units of every single term and every single quantity in term one. And these centimeters will cancel with those centimeters, and these centimeters will also cancel with those centimeters. So notice that this first quantity overall has units of neutrons per unit volume, per unit time, and now also per unit energy. So, and that's really what we would see for every term in this equation is that it has units of neutrons per unit volume, per unit time, and per unit energy. So these are all basically reaction rate densities per unit energy. Each term in this equation is a rate density per unit energy. And so you could kind of play a similar game by it would probably be a good practice to make sure that you can, knowing what these terms are, that you could work out and show that each of these overall terms has these units. Um, this scattering cross-section one is a kind of a tricky one, so I'll show that one too. Um, the the energy dependent scalar flux that again has units of neutron path length per unit volume per unit time per unit energy. The sigma s, the scattering cross section, did you go from E prime to E? That is like my probability density function times my scattering cross section. So that's my differential scattering cross section, which means it has units of 1 over centimeters, inverse length and inverse energy. But then DE prime also has units of energy. That's like an energy width. So that has units of energy as well. And so if I have all of those terms, then these EVs cancel those EVs down there. These centimeters here cancel those centimeters right here. And then notice that I have units of overall neutrons per unit volume, per unit time, and per unit energy. So it'd be a really good practice to make sure that you could work out why each of these quantities overall has those units. If you have any questions about it, definitely let me know. In each of these terms, we could give it like a physical name that kind of tells us some context about what the equation is representing. So this first term that has the diffusion coefficient and has the divergence of the gradient, that's like my net leakage term. So this would be my net leakage rate density. And it's a density, and now it's also a density per unit energy, because it's got those units of neutrons per unit volume, per unit time, and per unit energy. That second term, it's got a sigma t. So this is like my total interaction rate density per unit energy. Total interaction rate density per unit energy. Term 3 tells me about neutrons that are scattering from all other energies E prime into my current energy E. So this is what I'll call my N scattering rate density. My N scattering rate density per unit energy. And then last but not least, I have the term that is basically telling me about my fission production. It's telling me about the neutrons of all energies E prime that are producing neutrons of energy E. So this is my fission production rate, and I'll just call it my production rate density. Production rate density. And again, it's per unit energy. So the energy dependent diffusion equation, this is what it looks like. This equation is very difficult to solve for anything except very simple problems. So like if you were trying to design a real reactor, you probably wouldn't be able to use the energy dependent diffusion equation. So it's not necessarily the most useful thing to try to do calculations from, but it's still good to be able to understand the form of the equation, understand the individual terms, understand their physical meanings, be able to understand how each term has these kinds of units. But ultimately, if we're trying to do stuff with this equation, we're going to have to make some simplifications. And so in practice, What we would kind of do instead is instead of trying to solve this equation as it is, we would take this equation, we would integrate over some small energy range, and then we would kind of set up terms that are averaged over those different energy ranges. And then instead of having to solve this equation, we might do like a multi-group model. And that's like in practice what a lot of like core design software. Like if you guys end up taking Newen 418, which is the Reactor core design class, they use a program called Casmo and Simulate, and those programs solve a 8-group diffusion equation. So it's kind of like taking this equation, integrating it over an energy range, and then having 8 different energy groups by which you do calculations within those groups. Um, so I'm going to kind of start getting into how we could simplify the equations in that way to go from an energy dependent model to a multi-group model. Um, and so if we wanted to solve that steady state, if we wanted to find a solution to this energy dependent diffusion equation, our solution is going to be for the flux as a function of position and energy. Um, It's not time dependent, so there's no time argument if it's in steady state. And so if this is what our solution looks like, then we can do something kind of similar to what we did when we looked at the time dependent, space dependent problem, like with one group diffusion, where we said maybe we can solve this problem if we assume that our flux is a separable function, separating it into 2 different functions, one that depends on one variable and one that depends on another. And that's kind of like what the first fundamental theorem of reactor theory says, is that this neutron distribution in terms of space and energy is separable. So we could take that phi of R and E, and we could separate it into a spatial shape function, R of R, and then an energy distribution function that I'll call big phi of E. So we're just kind of doing another separation of variables. And we're gonna, I mean, if you got a PDE, that's basically, those are your options. You can try to separate variables or you can give up. So we're gonna separate variables. R of R would be the spatial shape function that would look just like those, the solutions to that problem would look just like what we saw for one group diffusion. And then we've got this energy spectrum function that we want to talk about now. And so the main difference between this approach is that we have to decide how we want to normalize that energy distribution. The normalization is arbitrary, but the most common way is to normalize this such that this shape function is exactly equal to our total scalar flux. So our total scalar flux phi of R, by definition, the way that we would get the total scalar flux is we would integrate the energy dependent scalar flux over all energies. So this is just a by definition thing. But then now we're saying this energy dependent scalar flux can be broken up into a function of space and a function of energy. So I'm going to rewrite it using that definition. I'm integrating from 0 to infinity of R times big phi of E, and then I'm integrating with respect to the energy E. And so notice this is an energy integral, and the space function is inside of that energy integral. A function of space doesn't have any energy dependence, so it can just be pulled out in front of that integral. So the space function can come out, and I've still got that energy integral left over. So I've got the energy spectrum function integrated over all energies. So based on our choice of normalization, what does this energy integral have to be? What is, if I were to do 0 to infinity of this energy integral dE, what does that have to equal to such that my scalar flux is exactly equal to that space function? What does this energy integral have to be for my scalar flux to be exactly equal to that space function? Has to be one, right? So that's our choice of normalization. We're going to assume that if we integrate that space, that energy function over all energies, that by definition, that energy integral is equal to one. And if that energy integral is equal to one, then that's exactly what we would want for our scalar flux to be exactly equal to that spatial shape function. And technically, there would be like a flux magnitude up front here. But because our original equation is homogeneous, you could put any constant up front that would end up satisfying the equation. But in general, the full form of this equation, you would have a C of phi times that shape function times that energy distribution function. And that flux constant or that flux magnitude you would find from something else. Just like in one group diffusion equation, you could find it from the power, you could find it from some other quantity like a leakage rate or an absorption rate or something like that. But yeah, this is just kind of like a by definition thing that is going to be helpful for us to keep in mind as we move forward. So like if we wanted to find that C of phi, we would need some other quantity, like maybe if we knew the reactor power, then we could determine what that flux constant was. And so by definition, if we have an energy dependent scalar flux, then the way that we would get the power, when it was the regular scalar flux, we would have like a fission rate density. And then if we integrated that over the volume, that would be what give us the fission rate. And then if we multiplied by E sub F, which is the number of, which is the energy per fission, then that's what kind of gets us from a fission density into a power density. And then taking that power density and integrating over the volume gave us the total power. But now our flux also depends on energy. So we have to also integrate that flux over all energies to determine what the total reactor power is. So this is the definition of power if we have an energy dependent scalar flux. And then here I'm just rewriting that scalar flux as a flux magnitude times that shape function times that energy spectrum. And notice that the EF and the sigma F and the C of phi in this case are all constants. So they don't depend on space or on energy. So those can all come up front. So I'll have C of phi, EF, sigma F up front. The spatial shape function doesn't depend on energy, but it does depend on position. So I'm going to take this shape function and put it inside of my volume integral. So I've got an integral over the volume of my core. I've got my shape function R of R, and it's integrated with respect to the volume of my core. And then all that's going to be left over in this integral and is in the energy integral is 0 to infinity of my phi of E dE. But then what we just said was that we are normalizing this whole quantity such that this integral is 1, right? So in that sense, this ends up simplifying because this whole thing right here is equal to 1. So therefore, my fission power, PF, is really just, again, it's a C phi times an EF times a sigma F times the volume integral of my shape function, D. So in this sense, the way that I would get that flux constant is the same way that I would get it in one group diffusion theory, which kind of makes sense if you think about the power being a integral quantity. Like the reactor power, it's the power caused by neutrons of all energies. So to get that, really all I need to do is integrate over the shape function. I don't really need to integrate over the energy distribution because all of those that whole energy distribution is going to end up effectively being normalized to 1. But yeah, if you have phi of E, and remember that that phi of E is a path length rate density per unit energy. So if I want to take this phi of E and convert it into a fission power, I have to multiply by the fission cross section, I have to multiply by the energy per fission, and then I have to take that entire energy dependent power density, and I have to integrate over volume, and I have to integrate it over energy. And depending on what you are given in the problem, you could find that flux magnitude accordingly. Basically, when you're dealing with this, you really just want to be careful about your units and making sure that the units on each side match up. In general, in the case of energy dependent diffusion, that flux, our total flux, is going to have units, and therefore our shape function is going to have just like normal flux units. And then that energy spectrum can have arbitrary units that just make it so that the units on the left side and the units on the right side match up. I think that is where, because we get out at 3, right? Yeah. I I think I have too many slides to try to wrap up the rest of what I wanted to talk about. So I think I'm going to stop my lecture right there. Do y'all have any questions? Um, It's going to be all of the lectures before the exam. So in this case, today we're on lecture 6. Tomorrow we'll do lecture 7, and it'll cover everything from lectures 1 to 7. And yeah, up to problem set 3 as well. If y'all don't have any questions for me, then I have some questions for y'all. Um,